Hi, my name is Misha, and I will be your second instructor for the anomaly detection training. My background is originally in math and physics, but now I'm an lead AI researcher at Applied AI, and I've been in AI and programming for the better part of 7 years. After Farid has introduced you to the general techniques of anomaly detection, I will discuss the extreme value theory and its relevance for anomaly detection with you later. As part of this course, you will have the opportunity to talk to the instructors and ask your personal questions. We encourage you to go through your own projects to try to apply the techniques that you learned here there, and also to ask us questions about the newest research in anomaly detection. In this last part of the anomaly detection training, we're going to talk about the extreme value theory. It's an often overlooked topic, and you might not have heard about it before. Anomaly detection and extreme value theory are highly related, but they have slightly different focuses, and it is easy to be confused about when which technique can be applied. Extreme value theory usually deals with tales of univariate probability distributions. Anomaly detection, on the other hand, deals with events that are rare but not necessarily large. Therefore, the topic of anomaly detection is more general than extreme value theory. Despite the smaller applicability of EVT techniques, there is still a valuable addition to the anomaly detectionist's toolbox. In several situations, anomalies directly correspond to large deviations from something. It could be a deviation from the mean of some sensor data, it could be the number of calls in an intrusion attack, or something else. An anomaly detection technique will often provide somebody with a score that then can be used in an extreme value theory analysis. We will have an exercise about that at the end of the session. Let us have a look at the extreme value theory in a nutshell. EVT is a mathematical topic, and you will often find it in math books. The foundations of extreme value theory are based on two theorems. The first one, the Fisher-Tipett-Gnedenko theorem, addresses the asymptotic distribution of block maxima within a sequence of independent and identically distributed random variables. Don't worry if you don't fully understand what this means. We will elaborate on it in a moment. The second theorem of extreme value theory is the Pickens-Maxima-Dehaene theorem. It provides an expression for the distribution of values that exceed a threshold. Let's get the mathematical notation that will allow us to talk about these theorems in more detail. Let xi denote a sequence of IID one-dimensional random variables, and let the cumulative distribution function be f. We will also use x to denote one of these random variables. The nth block maximum is a function of these random variables, and thereby a random variable itself. It is just the maximum of x1 to xn. Given a scalar threshold u, the excess over the threshold is also a random variable, which is defined by x minus u. Let us discuss some examples of when these definitions could be useful. Extreme value theory originated out of the necessity of analyzing large events. One of the first of its applications was for the design of dams. There the engineer has to solve the challenge of how high the dam should be, such that the probability of the town overflowing with water is low. So the dam needs to be high enough for rare events like large waves, not to disturb it, but we also don't want it to be infinitely high and require infinite resources. So here you could imagine the axis to represent the height of waves in a month, and the block maximum over 12 months would be the highest wave in a year. In fact, such records were available very early on, and dam engineers could use them to inform their design. As an engineer, one might be interested in the maxima of multiple years to inform the decision of how high the dam should be. However, one would typically not be interested in the maxima of, say, 10,000 years, because the costs of building such a dam would not justify its benefits. Similarly, one might be interested in the probability of the wave exceeding a certain threshold. So if I decide to build a dam of 100 meters, I would want to know how probable it is for the wave to be higher than that. This kind of variable, the difference of the height of the wave from the height of the dam, would be exactly the excess over the threshold. For some large n and some z denoting a large value of interest, we'd want to know the probability of the block maxima being smaller than the z. For the wave example, z would denote the height of the dam, and we want to know the probability of a wave in a certain amount of months to exceed that value. Similarly, focusing on the excess over the threshold, one might be interested in the probability of the excess over threshold being smaller than some variable y, where of course the excess should always be positive. As mentioned before, the theory is quite mathematical, so bear with me for a moment when I state the theorem exactly. If there exist sequences of real numbers an and bn, such that the probability distribution of the rescaled block maxima converges to something non-degenerate as n goes to infinity, then the non-degenerate distribution, which we denote as g of z, must be of the following form. This is a very particular distribution function. It is rare that one encounters new distribution functions in analysis. Most of the times, we are dealing with some variations of the Gaussian distribution. However, the extreme value distribution, which is this function g of z, it has qualitatively different behavior from the Gaussian. We will see how we can use it to inform our analysis. The distribution function has three free parameters. Thus, it forms a family of distribution functions, which is called the generalized extreme value distributions. The second theorem of extreme value theory is the Fisher-Tipett-Gnedenko theorem. It holds under exactly the same conditions as before, and for a threshold u going to infinity. We will see the meaning of that later. So under these conditions, the distribution of excesses over the threshold converges to a generalized Pareto distribution. As you see, it's a member of a two-parameter function family. The parameter xi in the generalized Pareto distribution is exactly the same as the parameter xi for the generalized extreme value distribution. So, the two cornerstones of extreme value theory are, first, an expression for the probability distribution of block maxima, and second, an expression for the probability distribution of excesses over some large threshold. Let us briefly discuss the practical significance of extreme value theory. Don't worry, the rest of this block will be about this topic, so you will have many opportunities to dive deeper. The convergence theorem from the first theorem of extreme value theory motivates the assumption that for large but finite n, there exists some constants an and bn and some parameters of the generalized extreme value distribution, such that the probability of the rescaled block maxima is well approximated by a member of the generalized extreme value distributions. Note that this approximal sign is very difficult to make quantitative. We just know that for infinite n, there would be exact convergence, but we don't exactly know how close we actually would be for finite n. While this first form is not super useful because we still have to rescale the block maxima with unknown parameters, it turns out that this is not a problem at all. In fact, one can simply redefine the also unknown parameters xi, mu, and sigma such that an and bn are absorbed into them. Thus, we obtain an expression for what we are actually interested in. The probability of the block maximum being smaller than some threshold is well modeled, at least that's our assumption, by a member of the generalized extreme value distribution family. Note that it does not matter that mu prime and sigma prime are different from the original mu and sigma. We didn't know the original values either. In a practical scenario, we will always find these parameters by fitting the right-hand side to a distribution determined by data. Thus, we will automatically find the optimal an and bn. The same analysis holds true for the distribution of excesses over threshold. Also there, the unknown an and bn can be absorbed into xi and sigma. Fitting xi and sigma to find a suitable member of the generalized Pareto distribution is sufficient to do an analysis for excesses over threshold. We will see examples of this immediately. Alright, now that you have seen the first parts of the theory, let's dive into the more practical things. Let's have a look at how extreme value theory can be fit to data and can help you detect anomalies. Before we load any data, let's get a feeling for how extreme value distributions look. Here we define a trainable generalized extreme value distribution. It has three parameters, xi, mu, and sigma,
we give initial values for them, and for reasons that will be apparent later, we can decide whether we want the xi to be trainable or not. The other parameters will be trainable. We use the TensorFlow probability API here, for the simple reason that TensorFlow already had the generalized extreme value function when we were writing this code. I'm not sure whether other distribution libraries have it by now. At that point, PyTorch did not. The libraries are very similar to each other, so don't worry if you prefer to use something else in your own code. This is an exercise that you can do partially on your own, but we'll start by doing it together. We want to see how different choices for xi, mu, and sigma affect the shape of the generalized extreme value distribution. What, for example, would happen if we send xi to 0? What happens if we move around mu? What happens if we adjust sigma? Just for the start, let's see. We take a positive xi and a positive sigma. Alright, this is how the function looks. It seems like it grows out of bounds out of our picture. Maybe we can increase the size a little bit just to see how it goes down. Okay, what happens if I move sigma? Okay. I invite you to stop at this moment and play around with the notebook yourself to get a better feeling. Now that you've played around yourself, maybe you have noticed the following behavior. Sigma controls the width of this function, right? Mu controls the positioning. Xi is a very important parameter. It controls the overall shape of the function. When xi is positive, the generalized extreme value distribution has a left boundary. The probability of points lying to the left of this boundary is 0, and therefore the value of the cumulative distribution function is also 0 there. This is reflected in this plot. If I extend the array a little bit more, it will become more obvious. When xi is negative, the function has a right boundary, and the probability of points lying to the right of that boundary is 0. The entire probability distribution has been exhausted at that point, and the value of the cumulative distribution function is 1 after that. Let's have a look. If I change the value of xi to be negative and re-execute the cell, we see the apparent right boundary, especially if I extend the width a little bit. If xi is negative, then the distribution has a right boundary. The probability of points lying to the right of it is 0, and the value of the cumulative distribution function after that point is 1. This is how the generalized extreme value distribution looks for the value of xi being equal to -2. As xi moves to 0 from below, the right boundary is pushed to infinity. Similarly, as xi approaches 0 from above, the left boundary is pushed to -infinity, and at xi being exactly equal to 0, the generalized extreme value distribution is equal to the Gumbel distribution, which has a value above 0 for all z. Let's see how it happens as we decrease the magnitude of xi. So now we will increase the value of xi going from -2 to 0. Here's how it looks for -2. -2 divided by 10. -2 divided by 20. And finally, as we go to 0, we see how the support of the function becomes larger and larger. Same for positive values of xi. Going from 2 to 0 from above looks like this. Now that we understand the qualitative behavior of the generalized extreme value distribution, we are ready to go to the data and try our first fit.
Before we fit anything, we need to load some data. We are going to use a taxi dataset that you might have seen before. Here we receive the number of calls per time. This dataset contains a number of calls per 30 minutes interval. We define some functions to normalize the data. In order to make use of the generalized extreme value distribution and the first theorem of extreme value theory, we will need block maxima. Here we have the number of calls per 30 minutes. We can group the calls according to dates and thereby obtain daily maxima and minima of calls. This will be the block maxima of 48 entries, because there are 48 30 minutes intervals in a day. Having these block maxima at hand, one way for detecting anomalies in this dataset is by fitting a generalized extreme value distribution to the distribution of these daily maxima. Before fitting, let's just have a look at the distribution by plotting the histogram. Here's how it looks. Can you already spot the obvious anomaly? What do you think caused them? I'll let you think about the question for a moment. Well, here's the answer. A suitable shape for fitting this data would be a distribution that has an upper right limit. This makes physical sense. There can be only so many calls in a day. This means we would expect a Weibull shape to make a good fit, with psi smaller than 0. Can also spot some obvious anomalies in the data, this point, and also this point. Just by looking at the histogram, they are well isolated from the rest of the data. Just by visual inspection, we can see the thresholds, how to filter out these points. The anomalies lie somewhere in values below -3 and above something like 1.8. By filtering the dataset and inspecting those values, we see the following date. There are only 5 of them. We can now look online for the meaning of those dates. The 2nd of November was a New York Marathon, and there was an exceptionally high number of taxi calls. New Year's is also an interesting day. It's not surprising that the number of calls was higher on New Year's as well. The 6th of February is Columbus Day, and there's usually a big parade in New York on that day. On the 27th of January, there was a big snowstorm. And finally, on Christmas, it seems that nobody would like to take a taxi.
Of course, visual inspection is not what we're after here. We want to be able to make use of extreme value theory, and we will fit the generalized extreme value distribution to the distribution of the block maxima, the empirical distribution of the block maxima. All right, let's do it. So first we will group the values and compute the daily maxima. Note that this throws away a lot of the values. We are just considering a maximum for a day, just one of 48 values. We will come back to that topic. We define a generalized extreme value distribution that can be fitted with TensorFlow probability. We give some starting point for the parameter psi. You will see in a moment why that's important. And we set psi to be trainable, so we will be fitting 3 parameters, psi, mu, and sigma. This is a very simple loop, performing gradient descent on these parameters. Let's see how it works out. Alright, we see that the negative log likelihood quickly decreases and reaches a plateau. After 100 gradient steps, we have already converged. Let's have a look at the result. Okay, so this is how the fit looks. It's not particularly good. This part to the right doesn't seem like it's optimal. It seems like the GAV is held back by this point. Before diving in further, let us visualize the convergence of the distribution. We will simply plot the distribution at each point of the fitting procedure, so at 100 points. And here we go. As you see, the distribution quickly centers around the empirical distribution, but seems to be really dragged to the right by this single point here. Why is that the case? let's get a little bit more intuition here. So, some live coding. I will now re-execute the code above with a different value of xi. So let me change the value of xi to be minus 0.05 and re-execute the fitting. This looks strange. The negative log likelihood plot is completely empty. What happened? Let's have a look at the first losses. Wow, so we started with infinity and then immediately arrived at not a number. That doesn't look nice. Let's try a slightly less drastic change. Okay, this time it got better. I want to figure out at which value of xi we actually start to get the diverging behavior. Again, we started off with infinity. Okay, trying something in the middle. Again, infinity. You see how extremely numerically unstable this fitting procedure is. Do you have a feeling for why? I will let you think on it for a moment. Here's an even more interesting situation. I've started with positive values of the loss, non-infinite ones, and then quickly the gradient steps turned the loss into infinity, and then none. Just after 3 steps we have diverged. If we look at the visualization of what has happened, we can understand the behavior. Here it is frame by frame. You see we start off at some reasonable distribution, and then after 1 step the distribution has moved to the left. However, it actually looks better than our previous fit. However, this point causes a very large loss, because it is now extremely improbable under this distribution. You have seen before that for negative xi, the generalized extreme value distribution has a support which has an upper threshold, which means for all values that are above that threshold, the probability will be exactly 0, and thus the loss, and thus the contribution of these values to the loss will be infinite. This is the reason for the numerical instability. It's the reason for the divergences. Due to that, gradient descent with a trainable xi is very unstable and should likely be avoided. We just got lucky in our first guess. To stress the point more, I will now adjust xi a tiny bit from minus 0.205 to minus 0.2. Now this time the training has converged and we get a good fit. We were lucky enough that the gradient descent has never led us to having exactly 0 probability for this point, so the loss could continue to decrease. There are a few lessons here that can be learned. Number 1, if you want to get a better fit, it would be better to remove the obvious anomalies. That might sound a bit counterintuitive. After all, we want to find the anomalies. After all, we want to use extreme value theory to find the anomalies. So why should we use another mechanism to strip off the obvious ones? The reason is that we want to capture anomalies or large values that are generated by the same mechanism as the other data. However, this very large anomaly with a value above 4 is caused by the New York Marathon, which is a very special event and is definitely not the same mechanism that generated the rest of the data. Removing this anomaly prior to the fit would allow the distribution to cover the center and the rest of the data in a better way. The other lesson is that gradient descent on xi is likely not our best option. If we are unlucky, then during gradient descent we might suddenly end up with an infinite loss and thus a non-recoverable situation. This is due to the hard threshold of the support of the generalized extreme value distribution. A clear strategy emerges. First, strip off the anomalies. Then, set the parameter xi to be non-trainable and only adjust the other parameters with gradient descent. In order to get a better fit, we can vary xi in a loop, and for each value of xi, find the best parameters mu and sigma. You can think of this as hyperparameter optimization for other machine learning procedures that you already know. Remember, however, that this is a very cheap operation, since we are only fitting 2 or a maximum of 3 parameters. This strategy of varying xi in a loop and finding the best mu sigma for each xi is an instantiation of the profile likelihood procedure. Another way of going about the problem of numerical instability and avoiding it would be to not use gradient descent, but some other procedure for fitting. We will not discuss such fitting procedures today, but we leave some references for you to explore. In the following practical exercise, your task is to improve the maximum likelihood estimation of the GEV. Remove the obvious anomalies and perform profiling in the shape parameter xi, or try using different initial values or learning rates for xi just by hand. Feel free to improve the code snippet given above by writing functions and making less use of the notebook state. You can evaluate the quality of your fit by visual inspection, as we have just done above, or by using a QQ plot. A short explanation of QQ plots will be given in a moment. You can also use any other statistical tools that you are familiar with in order to evaluate the quality of the fit. Finally, make use of the fitted model to find the non-obvious anomalies for the taxi calls. For the next exercise, you will need a statistical tool which is called the QQ plot. QQ plots are useful for finding differences between distributions and thereby evaluating the quality of a fit. A QQ plot is really rather simple. One just plots quantiles of one distribution against the quantiles of another. The quantiles of this empirical distribution of the dataset are given by sorting. If we have a dataset of n samples, then each data point corresponds to the k divided by n plus 1 percentile, where k is its order in the sorted dataset. With this knowledge at hand, and knowing how to transform percentiles into quantiles, you will be able to define a QQ plot for comparing the fitted distribution against the empirical distribution. If the distributions exactly align, the QQ plot will land on the diagonal. If they don't exactly align, you will see where the distributions differ. For example, here we see a difference for the lower quantile and some difference for the upper quantile, whereas everything in the middle is on a diagonal, which means we have a very good fit for the majority of the data and not a very good fit for the very few rare data points that are at the edges. So now, please complete the exercise by writing code that actually performs a QQ plot. Let us now discuss the solution of the fitting GEV exercise. We define a function that can fit any kind of distribution on the data, and then we define a function that loops over the values of xi that we want, retrieves the relevant distribution, fits it on the data, and computes the loss. We find the optimal distribution by finding the overall minimal loss of that procedure. We also split off the obvious anomalies by removing the values with the daily maxima smaller than 1.8 and larger than minus 3.5. This part is not very rigorous. After all, what is the right threshold? After doing this, we are left with one point which could arguably be an obvious anomaly. However, for now, let's treat it as if it was created by the same mechanism as the data, which stands in contrast to the data points that we have removed, like the New York Marathon, which was an exceptional event. Now, we apply the profile likelihood fit. We decide to investigate 50 evenly distributed values of xi in the range from -0.3 to -0.5. Note that we will declare xi as non-trainable, thus only fitting mu and sigma. In the end, after the profile likelihood, we find the best value of xi and the corresponding best values of mu and sigma. Despite trying out many xi's, the procedure is rather quick, since we are only fitting two parameters. Per choice of xi. We end up with a much better fit and a much smaller loss. If we were to have the optimal xi from the beginning, this is how the losses would look. Compare to the losses of the non-optimal xi without having removed the anomaly. We can analyze the quality of the fit with a QQ plot. You see that the bulk of the data, which lies in the center, is very well approximated by the fitted distribution. The values at the top are also somehow well approximated. However, the low quantity values are approximated rather poorly. This is not a problem for two reasons. Reason number one is that there are comparatively few data points in this region, thus they are less important for the fit. The main reason, however, is that we will only be interested in the upper edge of the generalized extreme value distribution for our anomaly detection analysis. Therefore, this part of the distribution is just less relevant for our task, and it's not tragic that we don't get a perfect fit. Finally, after having a sufficiently good fit, we can make use of it. We will declare all points to be anomalous that lie above the 99th percentile of the GEV. This percentile roughly corresponds to the value of 1.54, and thereby we find one more new anomaly. Maybe you recognize this date. It is a night before the 4th of July, an important day for the USA. Thus, it is maybe not too surprising that there was an unusual high number of taxi calls on that day. Not very surprisingly, this date corresponds to the semi-obvious anomaly that we have already seen in this plot. An important property of the analysis that we have just performed is that it is probabilistic. We can get a very clear interpretation of what has happened if we are to believe the fit. For example, we can say that for 99% of the days, the maximal amount of taxi calls per 30 minutes will not exceed the threshold found above. Note that this value is normalized, so we could denormalize it to the actual number of taxi calls. This stands in stark contrast to a non-probabilistic anomaly detection algorithm, which would just give a threshold or filter out anomalies. The probabilistic interpretation of extreme value theory analysis can be an important tool for planners. For example, a taxi planner could use this information to decide how many taxis should be available for covering the majority of normal days. Another big advantage of the probabilistic approach delivered by extreme value theory is the possibility to make uncertainty estimation. In fact, we get confidence intervals almost for free. Since we fitted the GEV using maximum likelihood estimation, we can get uncertainty estimates using the Fisher information matrix. If you're not familiar with this concept, we recommend to read the Wikipedia article on the Fisher information matrix and the empirical variant of it. The observed or empirical Fisher information matrix corresponds to the second derivative of the distribution at the optimal parameters. Fortunately, it is very easy to compute using TensorFlow probability. Note that for something like a neural network, you would usually not be able to compute second derivatives because they would correspond to a very large matrix. However, because the GEV only has 3 parameters, this is actually just a 3 by 3 matrix. The covariance matrix of the parameters found by MLE is given by the inverse of the information matrix. We can interpret the diagonal entries of this matrix as the variances of the individual parameters, and thus taking a square root of them gives us something like the standard deviations. Your task now is to use these functions in order to include error bars into the QQ plots of the maximum likelihood estimates of the GEV. Your result should look something like this. Let us now discuss the solution. We take a rather straightforward approach. We compute the standard deviations of the parameters by the methods explained above. Then we simply add these standard deviations to the parameters and we subtract them, thereby finding something like the upper edge and the lower edge of the parameters in the one standard deviation space. We create the corresponding GEVs by using these upper and lower value coefficients, and then we perform a QQ plot for each of those GEVs. This gives us something like a one standard deviation confidence interval for the QQ plots. We see that there is relatively little variation for the bulk of the data, and there is slightly more variation at the upper edge. This is good, because the ideal fit, represented by the diagonal line, lies within one standard deviation. It might be surprising, however, that at the left edge, where the quality of the fit is the worst, we only have very little uncertainty. We can understand this by simply looking at the GEV. This left tail is largely unaffected by changes in the parameters, which mostly shift the center or the right edge. This leads to the very small variations in the QQ plot. As explained before, the poor quality of the fit in this region is not particularly important, as we don't have many data points and we're also not interested in this part of the GEV for our anomaly analysis. So far, we have only used extreme value theory to find anomalies corresponding to large numbers of toxicols. For a complete analysis, we would also be interested in anomalies corresponding to a very small number of toxicols. Note that the generalized extreme value distribution is only concerned with anomalies due to large values, so we cannot directly apply it to the minima. Fortunately, there is a simple solution. We can just take the negative value of the minima. Then the largest of those negative values will correspond to anomalies due to few toxicols. Your task now is to repeat the same analysis as above for the daily minima. So now the solution. As announced, we find the daily minima and we negate them. The distribution of the negative daily minima looks like this. Again, there are obvious anomalies. The new obvious anomalies that we have found correspond to New Year. Again, the New York Marathon is appearing. And special new dates, the 26th and 27th of January of 2015. During this time, there was a large snowstorm in New York and nobody could get out of the house, and therefore there were very few toxicols. This is a known anomaly of this dataset. After stripping off the obvious anomalies, the daily minima look like this. We can now guess a good value for Xi, or perform profile likelihood like shown above, and fit a generalized extreme value distribution. Here is how the QQ plot of the result looks. In the upper part, which corresponds to the part that we are interested in, it is not too bad. The 99th percentile corresponds to a threshold of 1.58. The anomalies identified by the threshold, there is one more anomaly in addition to the obvious ones that is found by this threshold, which is also related to the large snowstorm while almost no taxi calls were performed. Let us now contrast the extreme value theory-based analysis to a very common way of finding anomalies, namely through the z-test. The z-test roughly means that we expect some value to be distributed as a Gaussian and declare points that are improbable under this Gaussian as anomalies. The quantity to be analyzed here would be the means of the daily calls. We can plot them and we can declare some threshold that will be chosen both for positive and negative anomalies, because the Gaussian is symmetric. The big question here is, where should we put the threshold? Note that the assumption of a Gaussian distribution is clearly not a very good one, since the actual distribution of the calls is highly skewed. Just by looking at the plot, it seems that 2 would be a good threshold. By choosing the threshold, we detect some obvious anomalies. For example, we see the New York Marathon, we also detect the snowstorm, and we detect Christmas. There's a new date that we haven't seen before, the 27th of November. It is close to the arbitrary threshold that we chose, and it's unclear to me whether it will actually be an anomaly and whether there is anything special on that day. One of the main downsides of the z-test is that we don't get any plausible probabilistic interpretation of the results. A Gaussian is simply not a good fit for this distribution, and the symmetric threshold does not have an appropriate probabilistic meaning. Alright, after playing with the distributions, let's take a look back at the theory. What have we really done, and why does it work? What kind of guarantees does the theorem give us about the quality of the fit? This is really the only thing that we care about. Well, unfortunately, the truth is we don't get many guarantees, if any at all. Let's start at the beginning. The block maximum, as you might remember, is just the maximum of x1 until xn, where all xi are just repeating the same event. Now, we were modeling the probability of the block maximum being smaller than some value. Now notice the following exact equality. Since all the variables are independent, are the same variable, the probability of the block maximum being smaller than z is the probability of x1 being smaller than z and x2 being smaller than z, and finally all the variables up until xn being smaller than z. Since we want all of them together and they're independent, it just means the probability of x1 being smaller than z multiplied with the probability of x2 being smaller than z, and since they're all identical, it's just the cumulative distribution function to the power n. Something is already fishy here, right? After all, the cumulative distribution function has the entire information of the normal distribution function. It means the entire information about the distribution of x. From here it seems like I could take this nth root of the distribution of the block maxima and recover the normal cumulative distribution function. At the same time, in the beginning we said that the extreme value theory distributions only cover the behavior of the tail and not the full distribution. So what's going on here? Let's have a look at another sign that something strange is going on. Note that when n goes to infinity, the above equation implies the following. Since we're taking the cumulative distribution function to the power is n, and the cumulative distribution function is always a value between 0 and 1, the exact limit is that we will get 0 whenever f of z is smaller than 1, and we will get 1 otherwise. So we actually know the exact limit of the distribution of block maxima when we send n to infinity. Let us say that the maximal physically possible wave would be, let's say, 400 meters. If we wait long enough, at some point in the eternal time horizon, a wave of 400 meters will arrive. This means that the probability of the maximal wave that we have observed over a very, very long time being smaller than 400 will be 0, because at some point a 400-meter wave will arrive. On the other hand, the probability of the maximal size of the wave that we have observed being smaller than 401 meters will be 1, because we have just said that 400 is a physical limit, so we will never observe waves higher than that. Thus, we have a hard threshold. This degenerate distribution, jumping from 0 to 1 at exactly 1 point, can be seen as the limit of the generalized extreme value distribution. It corresponds to the normalizing constants an being exactly equal to 1 and bn being 0. This simple observation does not really help us to analyze the data. The degenerate distribution is not particularly useful. In fact, quick question for you. How many parameters does the limit of f to the power n when n is going to infinity have? What would we get if we were to fit this degenerate distribution to the data? Have you thought about it? I hope your answer was 1. This one parameter is the value at which the distribution will jump from 0 to 1. In the previous example with the waves, it will be the value 400, because at 400 meters the distribution just jumps from 0 to 1. Because 400 meters represent the physical limit of the height of the wave. So what would we get if we were to fit this degenerate distribution to some data, let's say some realistic dataset of wave heights over a period of time? Since there's only one parameter, the only thing we can do is to set the value at which it will jump to the highest observed wave value. For real data, it might be smaller than the physical limit, because during our observation of wave heights, let's say 500 years, we would have only seen 390-meter height waves instead of 400. Clearly, there's not much information to be gained from such an analysis. Maybe now you get a better feeling why the theorem was phrased with some parameters, or some sequences of parameters an and bn. We might have a chance, by introducing an and bn, to have a non-degenerate limit when n goes to infinity. Fact is that for the distributions of the data that we care about, we simply do not know. Maybe there are sequences that allow such a convergence, and maybe there are none. Note also that in real applications, we always care about modeling mn for some finite n, rather even for a fixed n0, which is the time horizon of our block. An arbitrary series of an and bn that at some point might help convergence when n is going to infinity does not address our needs for finite n. In fact, we do not look for such a series of an and bn when we are doing our analysis, right? What we did is we fit the generalized extreme value distribution to the data for this fixed and finite n0. In this way, we automatically find the best an0 and bn0 that minimize the difference between f to the power n0 of z, which means the cumulative function, which means the cumulative distribution function, and g of z, a member of the generalized extreme value distribution family. Clearly, g of z is more expressive than this degenerate limit that we discussed before, and it could provide a much better fit. So the question that we really care about is the following. How well does the best fit of g of z for a fixed n approximate the distributions f to the power n of z when n increases? One could be interested in the infinity norm or some other distance metric. This is not the same as asking how well g of z approximates some rescaled variant of fn of z with n-dependent normalization constants. In this latter question, the choice of normalization constants matter. In the former, it does not. The normalization constants are implicitly determined by the best fit for each n. Since for this distance at finite n, an and bn have been optimized, one can reasonably expect a relation of the type delta n being the minimal of all possible values. They are implicitly determined by the best fit at each n. Unfortunately, theoretical bounds of convergence for the quantity of interest delta n, which we want to decrease, are hard to come by. In fact, I'm not aware of any analysis of them. It will be difficult to perform. There are some bounds for quantities of the type delta n of an and bn. Have a look at the text to see what exactly this means. The intuition is that you would construct some sequences that would help convergence and then analyze the convergence properties. Notice that this is not what we do in practice, so these bounds are not really relevant. They are also rather loose and non-informative. For these reasons, the extreme value theorems should be seen as a motivation for selecting relevant distribution families rather than a rigorous approach. We can hope for the best and see how good the fit is, and this is pretty much all that we can do. The previous part was important to understand the limitations of this theorem. But after listening to it, you may wonder, how were the theorems proved at all? How is it possible that we obtain a limiting form for the expression without ever having convergence bounds? The reason that this was possible is that the limiting distribution of these renormalized maxima must have a very special property. It must be max stable. So the proof is a proof of existence and not a proof of construction, unfortunately. It is instructive to go through this part of the proof to understand the gist behind it. The max stability property is also helpful in practical applications. We have used it to remove the renormalizing constants an and bn from our analysis. A cumulative distribution function is called max stable if taking the nth power of the distribution is the same as finding some constants alpha and beta and renormalizing the random variable of the distribution. The simple part of the proof of the extreme value theorem is the following. One shows that if the desired convergence takes place, then the limiting function must be max stable. This goes a long way towards understanding why the proof works. One can easily prove that the generalized extreme value distribution is in fact max stable. The other part of the proof is to show that it is the only distribution which is max stable. This is much harder, and we're not going to ask you to do that. From the first theorem of the generalized extreme value theory, it seems that increasing the block size before determining the maxima should improve convergence. However, in practical situations, increasing the block size would also lead to a decreased number of points for fitting, so it would increase the variance of the fitted parameters. Your task is to analyze the uncertainties of the fitted GEV after increasing the block size from 1 day to 2 days. Thus, even more data points will be thrown away. We recommend to use the reshape method on the already computed daily maxima and minima for finding the bidaily maxima and minima. What do you think about the result? Alright, so now let's have a look at the solution. As suggested, we compute the bidaily maxima by using the reshape function. Here's how the distribution looks. We fit the GEV by starting with a reasonable value of xi. This is how the loss looks like. According to the theory, the shape parameter xi should be independent of the size of the block. If you look back at the formulas, you will see that it is not affected by an and bn, the normalizing coefficients. However, since we find xi from fitting, of course we shouldn't be surprised to find a slightly different value than we have found above. We actually got a better fit than before, since now we have less than half of the loss with half as many data points. But this comes at a cost. We have now a higher variance in a very important parameter xi, finding the standard deviations of the parameters in the same way as we have done above, using the Fisher information. We see that the variance of xi increased from 0.026 to almost 0.04. So there will always be a trade-off between increasing the block size to have a better convergence of the GEV and having higher variance due to having too few data points. Apart from this, there might be modeling constraints. For example, you might be really interested in anomalous days instead of in anomalous 48-hour regions. For planning, one might require higher granularity, leading to smaller blocks and thus potentially a worse fit of the GAV. Let us now discuss the second theorem of extreme value theory and the method of peak over thresholds to which it leads. So far, we have only discussed the first theorem of EVT, which applies to the distribution of block maxima. As you might have noticed from the previous exercises, this can be somehow wasteful when it comes to data efficiency, because from each block we're taking a single data point. The second theorem of EVT gives rise to a more efficient approach. A short reminder of what the theorem states. Under the same convergence conditions as in the first theorem of EVT, and for a threshold u large enough, going to infinity, forgive me, this should have been infinity, the distribution of the excesses over the threshold x minus u, given that x is larger than u, converges to a generalized Pareto distribution, which is this function. Note that this approximates directly the excesses over the threshold. There is no grouping in blocks and no block maxima, so this equation can be used to estimate the entire tail of the cumulative distribution function f of x. To gain some intuition what can be done with this result, first note that for a single threshold u, we can generally approximate the cumulative distribution function through sample statistics. Just counting the number of samples with values exceeding u, let's denote it by nu, divided by the total number of samples, gives us an approximation of 1 minus f of u, where f is a cumulative distribution function. Those samples exceeding u will be called peaks over the threshold, and nu is their count. Quick question. What should u in the dataset fulfill in order for the above approximation to be valid? The answer is that u should be sufficiently small for many samples to exceed u, such that nu divided by n is actually representative of a probability and doesn't have too large of a variance. If u is too large, then very few samples will exceed it, and therefore the estimate of 1 minus fu by counting these samples will be unreliable. We can now perform a series of approximations to get directly to the tail distribution. First, using this equation, we can estimate that the probability of x larger than z can be expressed as nu divided by n times the probability of x larger than z, given that x is larger than u. This last expression makes it possible to use the generalized Pareto distribution theorem to approximate probability of x larger than z given x larger than u is the same as probability of x minus u larger than z minus u given x larger than u, just subtracting u on both sides, which is exactly the form that is covered by the theorem and thus well approximated by the generalized Pareto distribution. Plugging these two approximations together gives us that the probability of the tail p of x larger than z is well approximated by the counts of peaks over the threshold u multiplied by the generalized Pareto distribution. Intuitively, what does u need to fulfill for both approximations to hold? Well, for the first approximation, u needed to be sufficiently small for nu over n to be meaningful as an approximation for the CDF. However, u also needs to be large enough for the generalized Pareto distribution to be a valid approximation of the tail behavior, which is strictly only valid in the limit of u going to infinity. Thus, u needs to be large enough such that the values that are larger than u are governed purely by the tail behavior of the distribution and no longer by any specifics. In practice, it may look like this. If you have a probability distribution that looks like this, and then some point entering the tail behavior, where this might be the value x, and this is p of x, then a suitable value for u might be somewhere here. we still have enough samples on the right-hand side of U, but their behavior is no longer governed by the specifics of the distribution in the middle, which might have multimodal behavior. The Pareto distribution does not have multimodal behavior, and therefore is not suitable for modeling this part in the middle. We will make use of the generalized Pareto distribution and the possibility of expressing the distribution of peaks over the threshold with it in the next part of this module. Previously, in the theory part, we have discussed the second theorem of extreme value theory, leading us to the generalized Pareto distribution. We will now use the generalized Pareto distribution, or the GPD, as an approach for anomaly detection. Arguably, it's a more powerful approach than the generalized extreme value distribution based one. You will see why, and you can make your own opinion about it. Often, the two approaches will complement each other. The whole part of the generalized Pareto distribution for anomaly detection is phrased as a long exercise. Using the theoretical results explained before, find an approximation of the function p of x larger than zq as a function of the threshold zq for the number of taxi calls per 30 minutes. What would be the relation of this quantile to the quantile of the generalized Pareto distribution? Select some threshold u and fit the generalized Pareto distribution to these peaks over thresholds. You can determine anomalies from the quantile function by using a probabilistically inspired threshold. Think about what advantages you see from fitting the generalized Pareto distribution with the peak over threshold method compared to fitting the generalized extreme value distribution using block maxima. What are the disadvantages? Check for the quality of the fit, like you have done before, and perform an uncertainty analysis. Now let's discuss the solution of this whole block. As before, we define a factory of distributions. Here we only have two parameters, xi and sigma. Xi plays the same role as before, and we will also face the same difficulties for fitting psi as before. The generalized Pareto distribution is fit directly on the thresholded data on the tail of the distribution. So there is no need for grouping, and there is no need to determine daily maxima or general block maxima. Previously, when we did compute things based on the block maxima, we threw away data from every day except the maximum. Now we also have to throw away data because the generalized Pareto distribution can only model the tail behavior of the distribution. Remember, the threshold u needs to be large enough for the assumptions leading to the second theorem of extreme value theory to hold. Looking at the plot, we can make an informed decision of which threshold we would like to choose. Here it seems that starting from the value of 1, we start exhibiting the tail behavior, and the specifics of the distribution no longer matter after that point. This part corresponds to the conditioning in the second theorem of extreme value theory. We consider the number of calls given that the number of calls are larger than the threshold. This distribution is precisely the distribution of peaks over the threshold. As before, we have some obvious anomalies. Note that the histogram is quite different from the histogram of block maxima, since we have no more grouping. Thus, we might have multiple data points for a single day. We can say that the obvious anomalies appear after u plus 1, corresponding to the value 2, since previously we chose u, the threshold, to have the value of 1. As one might expect, we get multiple entries for the same day. The anomalous days that one finds is again the day before the 4th of July, Columbus Day, the marathon, and New Year's. After filtering out the obvious anomalies, this is what the histogram looks like. We can now fit the generalized Pareto distribution. We could do profile likelihood like we did before, or take an informed guess on xi, but in fact what we will do is we will use the value of xi found above using the generalized extreme value distribution. From the theory, it follows that this value of psi should also be optimal for the generalized Pareto distribution. So there is only one parameter to fit, sigma. Let us do so. The fit is extremely quick, the loss converges, and this is how the fitted generalized Pareto distribution looks. It looks sort of reasonable. We see that we have found a value for sigma of 0.45. As before, since we are dealing with an exact probabilistic modeling, and we can find the standard deviations for sigma and plot the QQ plot together with the confidence interval. Here is what it looks like. Note that for distributions of this form, the QQ plot will always start with a perfect fit at 0, 0. It looks reasonably good, even though the diagonal does not lie within one standard deviation at almost any point. This is somehow disappointing, but it is well reflected by the image that we have observed above. I leave it up to you to decide whether it's a good fit or not. As before, we can have a look at the 99th percentile and thereby make an informed decision on a threshold. The threshold corresponding to the 99th percentile as determined by the fitted generalized Pareto distribution is 1.87. We can have a look at the entries that exceed it and thereby catch possible anomalies. Apart from the obvious anomalies that we have seen above, we found new candidates. For example, the 10th of January 2015, which is represented through these two entries. It is difficult to say what exactly happened at New York during the day. I have tried. The 10th of January 2015 was the day following the Charlie Hebdo-related terrorist attacks in Paris. There was a large march in Paris, but there might have been additional movement across New York's large Jewish community. See, for example, this article that supports this hypothesis. Other days were found through this analysis: the 18th of October and the 22nd of November 2014. I was not able to find events that could have explained them. This analysis gave us a probabilistic model for the tail of the number of calls per 30 minutes. It is much more granular than the probability distribution of block maxima for a whole day. This kind of distribution might have more utility for planning taxi availabilities throughout a day and not just on a per-day basis. Finally, before concluding this last part of the Anomaly Detection online course, let us discuss how this kind of analysis can be applied generally. The taxi dataset was very simple. In many scenarios, we would want to analyze anomalies of different kinds related to vector-like quantities, for example, values collected with different sensors. Extreme value theory cannot be applied directly to this. However, as mentioned before, extreme value theory can be applied to anomaly scores that were determined with another anomaly detection algorithm. Using the tools outlined in this notebook, you can obtain a meaningful probabilistic model of the distribution of these anomaly scores, and thereby answer the often difficult question of where to put a threshold. More than that, this kind of analysis can enable planning that wouldn't have been possible without a probabilistic model. Finally, as a last part of this block, let us discuss some more advanced topics in extreme value theory. We will not cover these topics in depth. It's just an exposition for you to facilitate you diving deeper into the topic. One important topic for anomaly detection is time dependency. You have previously seen that a standard application of anomaly detection techniques is to time series, and time series are often time varying. Time dependency can be taken into account in extreme value theory analysis, but only to some extent. For example, one might attempt to form a fit with time-dependent parameters. There exist several strategies for fitting such functions to the data. A very simple one is if you know the time dependency of the parameters, or rather you know the modulation. For example, if you know that the center of your distribution moves according to a sine wave, and the only thing you need to find is a constant multiplying the sine wave, then you can use a sliding window strategy to find the maximum likelihood estimation fit of this parameter. However, it's very simplistic, and knowing the modulation is often not something that you have in practice. If you are interested in reading up on extreme value theory, you might find some incorrect claims in the literature. These incorrect claims are often related to trying to apply an extreme value theory to multivariate distributions, or to multimodal distributions. We have previously seen that extreme value theory is only concerned with tails of univariate distributions. The foundations of extreme value theory cannot be easily generalized to deal with more dimensions. They also completely ignore multimodality because they're only interested in tail behavior where modes simply disappear. You might stumble on literature that tries to apply EVT techniques to the cumulative distribution function of the Mahalanobis radius in higher dimensions. This tends to fail, in part because the Mahalanobis radius is dimension dependent. The other part why it fails is simply that EVT techniques are not constructed for this case. The other reason why it might fail is that EVT simply does not work for higher dimensional distributions, and thus one cannot apply the same formulas. There is simply no mathematical foundation for it. The application that we have seen, the New York taxi data, is very simple. We applied extreme value theory directly to the data. As said before, for multidimensional datasets, it simply will not work. However, virtually all anomaly detection algorithms will produce some one-dimensional score, the anomaly score. This one-dimensional score has exactly the semantics that something is an anomaly when the score is large. One classical task of ID analysis would be finding a threshold such that values with a higher anomaly score than the threshold would be indeed classified as anomalies. Finding such a threshold is non-trivial, and it is here where EVT can shine. Since the score is a one-dimensional variable, all the premises of EVT are fulfilled. Therefore, extreme value theory can be used in conjunction with other anomaly detection techniques. It is a valuable contribution to the anomaly detectionist's toolbox. We invite you to solve the following exercise. Choose any anomaly detection technique from the previous parts of the workshop and choose a dataset of your liking. Compute anomaly scores and treat them as an input for fitting the univariate extreme value distributions. You can apply either the generalized extreme value distribution or the generalized Pareto distribution, or, as shown here, try both of them. This exercise is left to the reader. However, it is likely precisely this procedure that you would use for solving a real anomaly detection task. Thank you for your attention. This concludes the extreme value theory part of our anomaly detection training, and in fact concludes the whole training at all. We hope the information was useful for you and you enjoyed the training. Goodbye. Let us mention some of the many things that we have omitted. The peak-over-threshold method can be adapted to work in streams in a memory-efficient way. There is a lot of literature concerned with how to improve on this. In particular, there are tricks for finding the best MLE fit for the generalized extreme value distribution as well as a generalized Pareto distribution. The fitting can be done in a much smarter and more robust way than what we have shown. However, the base ideas are the same. Maximum likelihood estimation is not the only way in which distributions can be fit. One can use other objectives, for example goodness of fit objectives, to minimize the differences between the fitted distribution and the empirical distribution.